Hi, I'm presenting our paper When Flames Feel Real in Augmented Reality, Effects of Plausibility and Placement of Virtual Flames on the Burning Hand Illusion and Physiological Responses. Lately, we have seen a lot of big investments going into the development of AR hardware and software. It's looking like AR is going to be ubiquitous in the near future, but this brings up a big issue we need to think about. As AR gets more advanced, we might start struggling to tell the difference between what is real and what is virtual. This could push us even further into what some call the hyperreal, a space where the lines between reality and virtual experiences blur. This is further exaggerated by one problem: our brains are emotional. When we see a snake, be it either real or virtual, our nervous system reacts immediately, leading to increased alertness by increasing our heart rate, skin conductance, pupil dilation, breath rate, and so on. We don't really know much about the possible cognitive and perceptual effects of augmented reality experiences, especially the rather extreme ones. These extreme AR experiences might not just be frightening, they could also have surprising cognitive and perceptual effects on us. Take, for example, AR. In their experiments, participants looked through an AR headset and saw realistic virtual flames engulfing their hand. Even though the fire was obviously not real and the AR setup rather clunky, some participants reported actually feeling heat on their hand. This is what we call a cross-modal illusion. Basically, it's when something you experience through one sense, like sight or hearing, ends up influencing how you process another sense, like touch. It can even trick your brain into perceiving something that isn't really there. In this case, seeing and hearing the virtual fire coming from your hand was enough to convince the brain that there was real heat, thereby inducing the involuntary heat sensation. The burning hand illusion, along with other undiscovered illusions unique to augmented reality, directly alter how we perceive our own body. This is something neuroscientists should take an interest in. Understanding these effects better could be important, not just for developing ethical guidelines and user interaction standards, but also for creating new kinds of pseudo-haptic feedback and other tools AR researchers might find useful. In our study, we wanted to dive deeper into the burning hand illusion. So, to better understand the burning hand illusion and how it emerges, we defined our first research question as: how does the burning hand illusion manifest in augmented reality? We don't just want to reproduce the findings of AR, but we also want to understand it by uncovering the two most likely important factors. First, the resemblance of fire, so basically the plausibility of the virtual stimuli. A green fire, for example, is probably less likely to be a plausible fire. And second, the location. We hypothesize that these heat illusions might not happen at all, or might be a lot weaker if you move the flames just far enough away from the hand, so they are no longer in direct contact with it. Here we move the flames just in between the hands. For the virtual flames to feel real, the emotional brain must perceive the virtual fire as a real threat to the hand. This means the virtual fire must be plausible and threatening enough to trigger corresponding autonomic responses. These can be assessed in a non-invasive manner by measuring changes in skin conductivity and pupil dilation. We hypothesize that these responses to be stronger compared to conditions where the fire is less plausible or not directly touching the hand. To answer these questions, we built the following experimental setup. We used the Vario XR3 for our experiment. The headset already features a calibrated integrated eye tracking system, which we use to measure the pupil dilation responses. It can track the pupil dilation with around 180 Hz and sub-millimeter accuracy. For skin conductance responses, we used the Groove GSR sensor. We implemented the software as well as the fire simulation inside the Unreal Engine. However, to answer these questions, we need to ensure that our AR system can accurately handle auditory and visual stimuli with minimal delays or asynchronies. So before this experiment, we compared several headsets as well as the Unreal and Unity engine. We found that some headsets and engine combinations have rather large stimulus onset asynchronies with large variabilities, making it impossible to conduct such a neuroscience study. If we have a difference of more than 10 milliseconds between when an auditory stimulus is presented and when a visual one is shown, it could already affect the outcome of such an experiment, leading to either unreproducible or wrong results. We have found that no system can meet these requirements without prior calibration and a specific combination of hardware and software. This calibration, the Vario XR3, and our software built within the Unreal Engine, we could get the onset asynchrony down to 3 milliseconds, which most likely did not influence the outcome of this experiment. We carried out the experiment in a soundproof, windowless room with carefully controlled lighting. Participants were seated at a table and we asked them to put their head on a shin rest while wearing the AR headset. We instructed them to place their hands on either side of a piece of paper which was matched to their skin tone. The reason for the skin-colored paper was to make sure the luminance and contrast were consistent for conditions where the stimuli appeared between their hands. We measured these skin conductance and pupil dilation responses to two audio-visual stimuli at two different locations. First, we had a realistic fire paired with a fire sound, and an implausible fire which was green and paired with a noise sound, whose spectrum we matched to the fire sound. Both stimuli were carefully calibrated based on the luminance and contrast to ensure they had the same perceived brightness. This was to ensure that the differences in pupil dilation were not just caused by the difference in color and perceived brightness between the conditions. Also, red and green stimuli have been shown to produce similar pupil dilation responses if controlled for perceived brightness. These stimuli were presented on either hand, were either on the hand or between the hands. We used an event-related design. A random stimulus appeared for 5 seconds, followed by a 10 to 12 second pause to let skin conductance and pupil dilation return to baseline. During the pause, a cue announced the next stimulus location, and participants were asked to focus their gaze there. After the experiment, we asked participants to self-report whether they had any sensations during the experiment. This was followed by a specific thermal sensation questionnaire that asked participants to rate the perceived thermal sensation on a scale from cold to hot for each condition. Please note that we did not tell participants prior to the experiment about possible involuntary thermal sensations. So for the results, overall 76% reported involuntary sensations. For the fire hand condition, 16 out of the 25 participants reported the illusion of heat, while 3 reported a tingling sensation. Interestingly, one person reported a cooling sensation when the fire disappeared. On average, the fire hand condition was perceived as slightly warm. When the fire was instead between the hands, 7 reported the illusion of heat, but the illusion was described as radiating from between the hands, so also affecting the left hand. For the green control condition, the implausible fire, the reports were ambiguous. 4 reported a heat sensation, 2 a cooling sensation, 1 a breeze-like sensation, and 1 even a rubbing sensation. No sensation was reported for the control between condition. Some participants reported that the illusion weakened during the experiment. One person noted that they became distracted due to the discomfort of the headset, which likely heightened their awareness of looking through the headset and consequently disrupted the illusion. For the skin conductance responses, instead of just analyzing the peaks, we modeled them using the PSPM framework directly on the recorded data and analyzed the model parameters. This approach gives us a more accurate estimate of the autonomic nervous system's input that drives these responses. In terms of preprocessing, We extracted epochs from -5 to +12 seconds, applied a bandpass filter between 0.0159 and 5 Hz, performed a Z-transform, and used a general linear model to estimate the average responses. Our analysis revealed that both the stimulus and location factors were statistically significant, with p-values below 0.01. We found that responses were consistently stronger in the fire conditions, particularly when the stimuli appeared on the hand. The most pronounced response was therefore observed in the fire hand condition. In contrast, responses were weaker when the stimuli were presented between the hands. To process the pupil dilation data, we first applied a low-pass filter at 5 Hz to smooth out any noise. Then we identified and removed any eye blink artifacts, filling those gaps using interpolation. After that, we performed a baseline correction using a reference window of -100 milliseconds before the stimulus onset. Finally, we standardized the data using Z-score normalization. For analysis, we focus on the average pupil dilation between 2 and 4 seconds after stimulus onset. This time window avoids the initial light reflex and captures higher cognitive effects. Our analysis showed that the only significant factor was location. It is surprising that we did not observe a significant difference between the fire and the green fire control conditions. So in conclusion, the burning hand illusion is highly effective at triggering involuntary heat sensations. When the fire was displayed directly on the hand, 76% reported feeling the illusion of heat. However, when the fire was placed between the hands, not touching either, only 28% perceived the illusion. Interestingly, those who did feel the illusion described it as if there was a real heat source between their hands warming both sides. When we reduce the plausibility of the fire by making it green and altering its movement to look less realistic, participants reported a variety of sensations, including warming, cooling, or even rubbing. These findings suggest that both the location and the realism of the flames play a critical role in the emergence of the burning hand illusion. The effect weakens when the flames are less plausible or are not positioned directly on the hand. In terms of autonomic nervous system responses, as we can see from the skin conductance and pupil dilation responses, the burning hand illusion triggers significant autonomic activity. We observed increased skin conductance responses, particularly when the virtual fire was directly on the participant's hand. Similarly, pupil dilation was more elevated in conditions where the flames were placed directly on the hand. However, we found no significant differences between the plausible and implausible fire conditions in terms of pupil dilation. These autonomic responses support the idea that the burning hand illusion produces physiological effects similar to those triggered by real thermal or threatening stimuli. This suggests that the virtual fire in the illusion is convincing enough to be perceived as a real threat to the hand, engaging the brain's homeostatic and emotional systems.